we were looking at uh, automata minimization, or rather DFA minimization, right? And here's the idea behind minimization. Number one, we already know that for any regular language, L, the DFA ML obtained from the equivalence relation RL is the unique up to isomorphism minimum DFA that accepts N. Okay, so we have shown this. And we also know that RM refines RL for any DFA N that accepts L, right? So because RM refines RL, each equivalence class of RL is the union of some equivalence classes of RM. So the idea behind minimizing a given DFA M, by that we mean minimizing the number of states, of course, is we merge some of these states merge states of M. And which states do we merge? Which we merge those states. Remember, each state of M is an equivalence class, corresponds to an equivalence class of Rm. So we merge those states of M whose equivalence classes, the union of whose equivalence classes is an equivalence class of RL. Okay, so that is the idea. Right? So merge Q and Q dash if and only if delta Q0 X equals Q and delta Q0 Y equals Q dash implies that X RL 1. Right? So that is the idea. Okay. So to implement this idea, we defined a relation called equivalence, also called indistinguishable, but we'll use equivalence on states of M, right? And that relation is denoted by these three lines, right? Three horizontal lines. So define the equivalence relation. On the states of M. So you are given a DFA. M. We define equivalence relation, this equivalence relation of the states of M. As follows. P is equivalent to Q if and only if for each X belonging to sigma star delta Px belongs to F if and only if delta Qx also belongs to F. Okay, and we say that P and Q are equivalent if P is related to Q and they are distinguishable if P is not related to Q, which means that there is a string X which takes the state P to a final state. Takes one of the two states P and Q to a final state and the other to a non-final state. So there are two cases. We see this, right? And then we say that these two are distinguishable, right? And we need to show given this definition, we need to show that this will give us the correct notion of equivalence. That is the correct, when to merge two states. So we need to show that if P and Q, two states, are equivalent in this sense, this is true if and only if for all x, for all y, delta Q0x equals P, which means that X belongs to the equivalence class in Rm corresponding to the state P, and delta Q naught Y equals Q, right? Which means that Y belongs to the equivalence class of Rm corresponding to the state Q. This implies that X, sorry, we are using the notation RL. So let me stick to that. That's all we need to show. If we can show that, then we are done. Then we can merge these states when they're equivalent. Okay, right? Because we just discussed that idea, right? When to merge. We merge two states when the corresponding equivalence classes in Rm of those two states go into the same equivalence class of RL. Okay. So this is what we have to show. And so this is so this is the correctness of this equivalence relation with respect to which states can be merged. Right? So and remember, this is if and only if. So implication must hold both ways. And this is really easy. And I leave the proof as an exercise. We have seen enough of the details. You just need to apply the definition of RL, right? And use properties of delta and delta hat to get this. Okay. So I'll not go through the proof. Okay. So this shows that the equivalence relation we have just defined, namely when two states are indistinguishable or equivalent, right? This is the one. This is the definition. This result shows that this is the correct notion of equivalence between states, based on which we can merge equivalent states and get a minimum state DFA, which is essentially the same as ML, right? Because there is essentially only one minimum state DFA, okay? which is ML. Every minimum state DFA is isomorphic to ML. Okay, so the next question is how to compute using an algorithm, how to compute this equivalence relation. Okay. How do we determine whether two states are equivalent? Where P and Q are two states of M. Okay. That is the next question. This definition by itself, right? This is the definition. Of equivalence. This definition by itself is not that useful. I mean, not directly. I mean, it doesn't give us an algorithm directly, okay? Because it looks as if we have to try out all strings, and that's not possible because the number of strings is infinite, right? So it doesn't give us an algorithm in a straightforward way. Instead, we give an inductive definition of the same relation, which immediately gives us an algorithm. Okay. So here's an inductive definition. Sorry, inductive definition of this equivalence relation. Okay. The base clause is if P belongs to F, and in fact, we define when two states are distinguishable. So we define the relation, which is the complement of this equivalence. So this is distinguishability. So the base clause is if P belongs to F and Q does not belong to F, or vice versa, then P is distinguishable from Q. Okay, that is the basis. And the inductive clause is if for some A, delta PA is distinguishable from delta QA, then P is distinguishable from Q. Okay, and of course, everything else if you cannot infer the distinguishability of a pair of states using these two rules inductively, then that pair is indistinguishable or equivalent. Okay, so this is an inductive definition, the same definition given here, but we need to show this. Okay. This definition is equivalent to the one given earlier. Okay, so this particular definition is the same as the one given here. And this proof is again, not a difficult proof, right? As you can imagine, the proof will be by induction. So this is again an exercise. As was this proof. So you have some work to do. You should work out these things on your own if you really want to understand how minimization works. Okay, and of course, the book gives the proofs, but in a different way, and I don't like the presentation on minimization in the book at all. It can be made much more transparent. Okay. But anyway, I leave that to you. You should read the book as well as work these things out on your own. Okay. So let me pause there. Do you have any doubts about anything so far about minimization? Uh, about any definition which is not clear? Or the idea behind minimization? Any doubts?
Excuse me, sir.
Yes.
Sir, in that need to show part, shouldn't P and Q also be reachable in M?
Yeah. Yes.
Okay, thank you, sir.
Uh, the so we are assuming that all the states in the DFA are reachable. So given a DFA M where all states are reachable, from Q dot, right? So to start with, we just delete all those states which are not reachable. Okay. And it is easy to verify that we still have a DFA, right? There will not be any missing transitions, right? So that's also an exercise. that if you throw away all the unreachable states, right, you still have a DFA. Okay. So we keep only the reachable states, and then we define this equivalence relation uh, on these states. Right? Okay. So let us proceed to the algorithm. So this inductive definition of distinguishability gives us an algorithm uh, for minimization. Given a DFA, we obtain a minimum state DFA or the minimum state DFA for the same language, right? So this is the algorithm. Right? Um, Essentially, we use the inductive definition to discover all pairs of states which are distinguishable, right? And uh, the remaining pairs which are indistinguishable, right? They are all merged, right? So if P is equivalent to Q and Q is equivalent to R and R is equivalent to S, and we merge all P, Q, R, S, okay? Whereas things which are indistinguishable are are kept distinct. So that is the idea. So the first step in the algorithm is eliminate, as I said, eliminate or delete all unreachable states from M. And a simple BFS or DFS will tell you which states are reachable and just throw away all the other states. Okay. And then we maintain a table of pairs. Okay. Uh, and just to give a name to that table, uh, this table is maintained in the form of this is a two-dimensional table, right? So, of course, you can think of an n by n two-dimensional table, but if P and Q are distinguishable, then so are Q and P, right? So we need to maintain only one half of the table, one side of the diagonal, right? That's all we need to maintain. And we know that each state itself is indistinguishable from itself, right? So we maintain either the uh, portion below the diagonal or the portion above the diagonal, right? And so let's give names to those variables. So uh, let's call this distinguish. This is a variable which maintains pairs of states which are distinguishable. So this is, sorry, I will not use equality here because I am not going to use C this is pseudocode. This is an algorithm. So this is initialized to all those pairs PQ, uh, such that P belongs to F and Q does not belong to F. And because we are maintaining only one half of the table, I don't need the other condition saying or P does not belong to F. Okay. And Q belongs to F. Okay. Because we'll maintain the table in this way, in this fashion. Okay. So if there are n states, say then the table will be of this form. Let's say the states are 1 to n. So the columns will be 1, 2, 3, and so on up to n. And the rows will have, we know that 1 is indistinguishable from 1. So we'll only have 2, 3, and so on up to n here, right? And finally here, no, we won't have n here. We'll have n minus 1. Right? This is what the table will look like, right? So if P and Q, if P belongs to F and Q does not belong to F, P and Q are distinguishable. Okay, this is the very first step. This is the initialization, which means that at the beginning, all final states belong to one class and all non-final states belong to another class. Okay. And we need another variable called old distinguish. And this is initialized to 0, right? So step 2 is just the initialization. Well, maybe I'll just number them 2 and 3. So 2 and 3 are initializations. We initialize these two variables, okay? Old distinguish will always be one step behind distinguish. And we need it because that is the terminating condition. We stop, we come out of the loop when there are no more changes, which means distinguish is the same as old distinguish. So while distinguish not equals old distinguish, oh, sorry, I'm using capital here. we set old distinguish. I'm not using the braces or begin end pairs here. I'm just using the indentation to mark the body of the loop. So all this is within the body of the loop. Old distinguish is assigned. This is an assignment. Distinguish. And then, so this is 5 and 6. There is a for loop here for every symbol. For every symbol A, and for every pair PQ, which is not in distinguish, meaning we have not been able to distinguish P and Q so far. So let me underline the control statements. So for all these do, right? So this is within the for loop. If the pair delta PA, comma, delta QA belongs to, again, I have to use capital here. So if delta PA and delta QA were earlier found to be distinguishable, then we add the pair PQ to the set of distinguishable pairs. Union, the singleton containing the pair PQ, right? And that's the end of the algorithm. So this is 7 and this is 8. So the for loop and the while loop both end here, right? And I should add a then here. Yes. So is the algorithm clear? I'm not asking about why it works, but the steps of the algorithm, are they clear? Do you have any doubts about that? Maybe you have some time to go through an example, at least a few steps, right? Just to briefly analyze the time complexity. And the correctness of this algorithm follows from this inductive definition. So if this inductive definition is correct, that is, it is equivalent to the one given earlier, then this algorithm uh, can be proved using a simple induction that it is correct, right? So I will not prove the correctness here. It all depends on the inductive definition, right? And so the time complexity, uh, what is the number of iterations of the while loop? Anyone? In the worst case, how many times will we go through the loop?
All the number of pairs.
Well, yeah, that is certainly a uh, an estimate because there are n square pairs, right? Um, well, order of n square, right? And because at each step, in each iteration of the while loop, uh, uh, we add at least one distinguishable pair. Otherwise, we stop. So that way, uh, uh, order of n square is an estimate, but it is the claim is it is too pessimistic, and you can actually do it in order of n. Uh, so can we see why this is the case? I leave that for you to ponder about. Uh, in each and the number of steps, number of operations in each, or rather the time, uh, the time taken in each. That is the same as the number of operations. This is uh, this is n square. In fact, it is order of the size of sigma, that is the alphabet, because you're taking for each, you're considering this for the for loop for each symbol sigma and for every pair, right? So this is indeed order n square. And therefore, the total time is, so I'll put a y here. This is for you to think about. And you are also doing a course on algorithms in parallel. So this is for you to think about. In this course, our focus is not so much on the complexity of the algorithms, but on the algorithms themselves, whether they exist or not, right? So I'll not go into these details, but it turns out more efficient algorithms exist, okay? So there is an algorithm that runs in time n log n or n log n. Okay, but we won't go into all this. Instead, we'll look at an example of DFA minimization. At least a few steps of the algorithm. So here's the DFA. Quite a few states, in fact. So I'll definitely not be able to finish A, B, C, D. There are 8 states. There's just one initial state C, final state C, and one initial state A, but there are more states E, F, G, H. E, F, G, H, and oops. So this is 0, 1, 0, 0, 1, 0. 0 and 1 and 0. This is a 0 here. And just have to make sure that no transition is missing. So E to H, this is 0. There's a 1. There's a 1 here. So anything else from F to C on 0. And 0, G 0, G on a 1. Where do I go from G on a 1? I have to check that. Something seems to be missing here. From G on a 1.
Sir, you're going to E.
Oh, yeah. Right. Yeah. So D on a 1. G on a 1. So is it complete now? It's become too cluttered. Actually, I should have drawn it with more separation between the states. But I just didn't think about that, huh? But anyway, so this is the DFA M. And we got to minimize the states, the number of states of the DFA, and so that it accepts the same language. So we just come up with that table, right? So this is the table which we call distinguish in the algorithm, right? Uh, well, it's good that I didn't draw it too big because then the table and the automaton will not fit, would not have fitted on the same screen. So there are pluses and minuses of every decision. So here's the table, right? So the columns are labeled A, B, C, D, E, F, G. So let me drop the rest of it, and from the bottom, H, G, F, E, B, C, B, B, C. Right? We don't need the diagonal elements because we know that those pairs are indistinguishable. I mean, every state is indistinguishable from itself. So these are the pairs we need. So, right? This may be an inefficient way of drawing this. See. Well, not sure what is an efficient way. Okay. That hardly leaves any time for marking the, so B, C, D, E. Whew. It's a bit cluttered here. So this is F, this is E, D. Ah, got it. Right. So in the beginning, remember C is the only final state, right? So and every other state is non-final. So we can distinguish C from everything else, right? So we put a cross here. Meaning these pairs are distinguishable. And similarly here. So the columns and rows corresponding to C, we put a mark. So all those pairs are distinguishable. And so far, nothing else is distinguishable. This is the initialization, right? If you go back to the algorithm, that is, distinguish is P belongs to F and Q does not belong to F. Yeah. Well, I think we do need to state the vice versa, right? I thought this was enough, but I think we need to put that, right? Okay, what is the next step? So the next step is look at uh, all the pairs which are not distinguishable so far, right? And see if there is a single symbol A that'll uh, take us to distinguishable states. So, for example, can we distinguish B from A? Well, from B on a 1, we go to a final state. And from A on a 1, we go to a non-final state, right? So for the symbol 1, and we already know that F and C are distinguishable, right? Look at this particular entry here. Because F and C are distinguishable, and delta B1 is C, and delta A1 is F, and F and C are distinguishable, we'll put a mark here, right? So that is how we proceed. So we just proceed in this way. And it turns out that at the end, B and E, B and E will be found to be indistinguishable. Is that believable? No, no, that's not the case. Huh? B and H. Is that the case? B and H. Yeah. So you can see that at the end, you'll see that B and so this pair will be indistinguishable, and A and E will also be indistinguishable, and F and D, these will be indistinguishable, but every other pair will be distinguishable, okay, if you fill out the entire table, okay? So you can merge these states A and E, and D and F, and B and H. If you merge these pairs of states, then you get a minimum state DFA. Of course, I didn't go through all the steps, right? You should do it on your own, okay? That is also an exercise. Okay, so that's the end of today's class.